Vertical stretching. Okay, as you read over this, I know the math language is a little hard to understand sometimes, so I put it in some plainer English for you. Basically what this says is that if you multiply a number to the function, that will cause the function to vertically stretch if the number is greater than 1. The larger the number, the bigger the stretch. Okay, here's an example of vertical stretching. We are starting with the graph that's drawn in black ink. And then the graph that's drawn in blue ink shows what happens when that graph is multiplied by a number c, which is greater than 1. You'll notice that the intercepts, the x-intercepts, have not changed. The y-intercept has, and the graph has gotten vertically longer. Here's an example on the screen of a graphing calculator. y1 is the graph of the absolute value function. And then you can see y2, 3, and 4 is the same graph with different numbers multiplied in front of the absolute value. Again, notice that the larger the number, the more it's stretched upward. Next we have vertical shrinking. And again, here's the way we explain it mathematically, but in plain English, what this says is that a number multiplied to the function will vertically shrink the function if that number is between 0 and 1. And the smaller the number is, the closer to 0, the more you're going to see that graph shrink. Again, here's another example. Like before, the original function is the one drawn in black. The one drawn in blue has been multiplied by a number between 0 and 1. Notice again that the x-intercepts have not changed. The y-intercept has, and you'll notice the graph is much shorter, much closer to the x-axis. Here's an example putting several graphs on the screen of a graphing calculator. You'll notice the original is y equals x cubed, and then each of the other graphs is what happens when it gets multiplied by different numbers. Notice that y2 has the smallest number out in front, and that is the one that is pushed the closest towards the x-axis. Now we can also stretch and shrink a graph horizontally. And this tells us how that works. Now, if you think back to what we were doing with the translating, if you added or subtracted a number to the function, it moved the graph up and down vertically. If you added or subtracted the number directly to the x, it moved the graph horizontally left and right. Stretching and shrinking kind of works the same way. With the vertical, we were multiplying a number to the function itself. It came before the f of x. Here, notice that we are multiplying the number to the x directly. And again, it's kind of an opposite relationship. With the vertical, the bigger the number, the bigger the stretch. With the horizontal, the bigger the number, the smaller the stretch. Okay, so this is a summary of the horizontal stretching and shrinking. A number multiplied to x will horizontally stretch the function if that number is between 0 and 1, and horizontally shrink the function if the number is greater than 1. Here are a couple notes about this stretching and shrinking. Vertical stretching and shrinking will not change the x-intercepts, and we notice that in our examples. It may change the y-intercept. Horizontal stretching and shrinking will not change the height, the maximum or minimum y values of the graph. It will also not change the y-intercept, but it could change the x-intercepts. And then this was what I was saying a minute ago. Remember, when you're multiplying to the function itself, that's going to affect it vertically. Anything multiplied to the x directly will affect it horizontally. Okay, so let's do an example. We're going to take this graph and we're going to stretch it by multiplying 1/2 times x. Give this a try, pause the recording, and then resume the recording to check your answer. Okay, notice what's happened here. We're multiplying by 1/2 x. What actually happens is that, as we said before, when that number's between 0 and 1, we have a horizontal stretch. So our x values are actually multiplied by 2 for the same y values. We had -1, -2, now it's -2, -2. Notice our y-intercept has not changed, but our x-intercepts have. Okay, we're also doing reflecting in this section. So here's a little summary of reflecting. It says for a function y equals f of x, the following are true. The graph of y equals negative f of x is a reflection across the x-axis, and the graph of y equals f of negative x is a reflection across the y-axis. Okay, this is really easy, again, to get these confused, so we need to get these down. It kind of helps to think about what's going on. When you're reflecting across the x-axis, you are changing out the positive y values for their negative counterparts. And when you reflect across the y-axis, you're doing the same, only with x's. Here's an example of reflecting across x and across y. And notice the points. On the first graph, we're reflecting across x. The original graph has AB as a point. The reflection has A negative B. So our y value has changed from a positive to a negative. On the one we're reflecting across the y-axis, the same thing happens, but with the x value this time. Okay, let's do this example. What you need to do is take this graph, and you're going to resketch it first as a reflection across the x-axis, and then as a reflection across the y-axis. Pause the recording, give this problem a try, and resume the recording to check your answer. All right, here's our graph of negative f of x. Notice that for every AB that was on the original, we have changed those to A negative B. So the only point that doesn't really affect, or 2 points, would be the point -4, 0, that stayed the same, and 0, 0, where it goes through the origin. Here's the graph of f of negative x, and for this one, if AB is on f of x, then negative AB is on f of negative x. In other words, we're leaving the y values the same as the original, but we're trading out the x values for their opposites. Okay, now it's time to combine all these transformations we've been talking about. But before we do that, it's really important to realize that order is crucial. You need to do these transformations in the right order. And that's really just as simple as following something that you learned a long time ago. In order to do the transformations in the right order, you're going to follow order of operations for that particular x value. In other words, if they're parentheses, you start inside the parentheses. Take care of exponents, anything after that. Just follow the order of operations. Okay, here's an example. We're going to describe how the graph of y equals -3 times the quantity x minus 4 squared plus 5 can be obtained by transforming the graph of y equals x squared, and you're going to sketch it. Pause the recording to try this and resume the recording to check your answer. Okay, here's what all those numbers mean. We're going to start inside the parentheses because remember, again, we're following order of operations and parentheses come first. Inside the parentheses, we have a -4, which is a shift of 4 units to the right. Next, we do multiplication, which is out in front. We have 2 things going on here. We have a vertical stretch by a factor of 3 and a reflection across the x-axis. And then finally, we finish it off with a shift 5 units up. Okay, here's the equation broken down into parts. First, we took the x squared and moved it right 4. Then we stretched it by a factor of 3. Then we reflected it, and finally moved it up 5. Here's a little bit more about the importance of order in translating graphs. It says the order is important, and changing the order of a stretch and shift can result in a different equation and graph. For example, the graph of y equals 2 times the absolute value of x plus 3 is obtained by first stretching the graph by a factor of 2 and then moving it 3 up. However, if you put the x plus 3 in the absolute value then what you have to do is move it first and then stretch it. You may not think this will make much of a difference, but let's compare the two graphs. This is the first one, 2 times the absolute value of x plus 3. And the second one, 2 times the quantity of the absolute value of x plus 3. Notice there is a difference. The fact that the 3 is inside with the x tells us to move it to the left in the second graph, but in the first graph, since it's outside and away from the x, we move it up. Okay, here's an example. This figure shows two views of the graph y equals the absolute value of x and another graph illustrating a combination of transformations. You're supposed to find the equation of the transform graph. So the graph in blue is the absolute value graph. Your task is to find the equation for the graph in red. Pause the recording, give this a try, and resume the recording to check your answer. Okay, looking at the red graph, it shows that the lowest point is at 3, -2, which means that we know the graph has been moved right 3 and down 2. The next thing we did was he took a point on the right side of the graph that had coordinates of 4, 1, and we found the slope of that side of the graph. That's going to help us figure out what got multiplied in front. So we have finding the slope gave us the stretch factor, which is 3. That's going to go out in front of the absolute value. So we have y equals 3 times the absolute value of x minus 3, then minus 2. Okay, now we have some classwork problems. Give these a try on your own, pause the recording as you do so, and then resume the recording to check your answer. Do that for the rest of this video.